4. Indexes. Created to speed up data retrieval. Certain indexes store data in a specific order. Without indexes, rows are stored randomly. Queries can explicitly specify sorting order. 5. Example of ordering confusion. User assumed rows were ordered by entry. Misunderstanding led to data duplication. 6. Tip. Always specify sorting order in queries if needed. Sorting large datasets is expensive, so avoid unnecessary sorting. 7. Optimization. Database engines use metadata and indexes to optimize queries for performance. Fragmentation and index choice can affect query results order. 8. Summary. Different use cases and intended usage patterns significantly impact database design and performance. Understanding and applying relational theory and data modeling techniques is key to efficient database design. Sorting large datasets can be expensive in terms of computational resources and time due to the following factors. 1. Computational complexity. Sorting algorithms have varying time complexities. The most efficient comparison-based algorithms, like merge sort, quick sort, have an average time complexity of \O n \log n \, where \n is the number of elements. For very large datasets, this complexity translates into significant processing time and resource usage. 2. Memory usage. Sorting large datasets often requires substantial memory, both for holding the data and for additional structures needed by the sorting algorithm. In-memory sorting might be infeasible for very large datasets, necessitating disk-based sorting, which is slower. 3. Disk I/O. When datasets do not fit into main memory, sorting algorithms must rely on disk storage, leading to increased disk I/O operations. Disk I/O is much slower than memory access, making the sorting process considerably longer. 4. CPU and resource utilization. Sorting large datasets can consume a significant portion of CPU resources, potentially affecting the performance of other applications on the same system. High CPU utilization might require more powerful and expensive hardware to maintain acceptable performance levels. 5. Distributed systems. In distributed databases, sorting often involves shuffling data between nodes, leading to network overhead and increased complexity in coordination and communication. Systems like Hadoop or Spark perform distributed sorting, but the overhead can be substantial, impacting performance and cost. 6. Indexing and database performance. Creating and maintaining indexes that support sorting can be expensive, both in terms of initial creation and ongoing maintenance as the data changes. Indexes themselves consume storage space and require periodic updates, adding to the cost. Examples of cost implications. Cloud services. Cloud-based databases like AWS RDS, Google Cloud SQL, or Azure SQL Database charge based on resource usage. Sorting large datasets can increase CPU and memory usage, leading to higher costs. Choosing higher performance tiers to handle intensive sorting tasks also increases costs. On-premises systems. On-premises databases require more powerful hardware to efficiently sort large datasets, leading to higher capital expenditure and maintenance costs. Best practices to mitigate costs. 1. Optimize queries. Avoid unnecessary sorting in queries. Use appropriate indexes to speed up sort operations. 2. Efficient indexing. Create indexes on columns frequently used in order by clauses. Regularly maintain and optimize indexes. 3. Batch processing. Break down large sorting tasks into smaller batches to reduce resource strain and improve efficiency. 4. Distributed systems. Use distributed data processing frameworks like Apache Spark for large-scale sorting tasks to leverage parallelism. By carefully considering these factors and optimizing data operations, you can manage and reduce the cost implications of sorting large datasets. Here is a breakdown of the provided text into key points. Managing and reducing sorting costs. 1. Consider factors. Carefully consider factors influencing sorting costs. Optimize data operations to manage and reduce costs. Pillar 2. Uniqueness in sets. 2. Mathematical set theory. A set is a collection of unique elements. Example, the set of uneven numbers includes each number only once. Axiom of unicity. 3. Application in databases. Unicity is useful in databases. Example, a customer table should store each customer only once. 4. Issues with duplicates. Storing duplicates leads to problems, e.g., inaccurate counts, incorrect reports. Example, counting customers or calculating sales per customer. 5. Technical challenges. Deleting a specific row is difficult without unique identifiers. Example, if 2 rows describe the same patient, deleting one without the other is challenging. 6. Ensuring uniqueness. Database administrators must ensure each row is unique. Comparing new rows column by column is time-consuming. 7. Use of keys. Keys enforce uniqueness. A key is a column or combination of columns with unique values. 8. Example of keys. Each car has a unique license plate. The vehicle table uses license plates to uniquely identify cars. 9. Contextual uniqueness. Uniqueness can depend on the table context. Example, a damaged table may have multiple entries for the same license plate, while the vehicle table will not. 10. Illustration. The vehicle table holds one row per car with a unique license plate. The damaged table shows claims, with some cars having multiple entries, non-unique license plates. Here is a breakdown of the text into its key points. Keys. 1. Defining keys. Databases do not automatically check rows for uniqueness. Checking rows column by column is expensive. Developers must define keys to check for uniqueness. Each table needs a key, and the developer decides if and which column will be used as the key. Types of keys. 2. Candidate keys. Candidate keys are columns that logically store unique values. A table can have 0, 1, or more candidate keys. Examples, license plate in a vehicle table, SSN in a person's table, ISBN in a book table. Candidate keys can be single columns or combinations of columns, e.g., postal code and house number. 3. Logical, business keys. Logical keys store values with real meaning and are necessary regardless of their use as keys. Example, SSN is stored by companies and can function as a key. Logical keys are used in everyday contexts to refer to objects, e.g., a course name. Caution: names are often not unique and can be risky to use as keys. 4. Technical, surrogate keys. Surrogate keys are created when there are no natural candidate keys. These keys are usually meaningless but unique. Database systems can generate surrogate keys, e.g., sequences, identity columns in SQL Server. Surrogate keys should be meaningless to avoid misinterpretation and flexibility issues. Examples, product numbers, account numbers, insurance policy numbers. Primary and foreign keys. 5. Primary and foreign keys. Two kinds of keys play crucial roles in databases: primary keys and foreign keys. Primary keys uniquely identify rows within a table. Foreign keys establish relationships between tables. Summary. 6. Keys in databases. Keys ensure uniqueness and aid in data integrity. Different types of keys serve different purposes and contexts. Logical keys have real-world meaning, while surrogate keys are system-generated and typically meaningless. 1. Row uniqueness in databases. Databases do not check rows for uniqueness automatically. Checking rows column by column is too expensive. The database developer must define a key for uniqueness checks. A key must be defined per table. Deciding whether a table requires a key and which column to use as the key is necessary. 2. Types of keys. Candidate keys. Columns that logically store unique values within a table. Examples include license plates, social security numbers, SSNs, and ISBN numbers. A candidate key can consist of multiple columns, e.g., postal code and house number. Logical business keys. Keys with real meaning that are part of the data, regardless of their function as a key. Essential for understanding data and processes, e.g., SSN for employees. Risky if not unique, e.g., names. Technical surrogate keys. Added columns with unique values when no suitable candidate key exists. Typically meaningless but unique. Created using database features like sequences or identity properties. Examples include product numbers, account numbers, and insurance policy numbers. 3. Primary and foreign keys. Primary keys and foreign keys are crucial in databases. Primary keys uniquely identify rows within a table. Foreign keys establish relationships between tables. 1. Primary keys. Introduction to primary keys is essential for understanding keys. Uniqueness of rows is checked based on one column designated as the primary key. The primary key ensures no duplicate values in its column, making rows unique. The primary key is a chosen candidate key for checking row uniqueness. Selecting primary keys impacts database performance and enforcement of uniqueness from a business perspective. 2. Foreign keys. Foreign keys introduce the concept of relationships between tables. A foreign key stores the primary key of one table in another table. The foreign key references the unique primary key value in the original table. This relationship allows specific, unique row references across tables. Example, an employee table with unique employee ID, primary key, and a payment table with employee ID, foreign key, to record multiple payments. Foreign keys enable combining rows from different tables while maintaining data relationships. Splitting tables using foreign keys is the basis of normalization, dividing data into multiple tables without losing relational context. 1. Role of primary keys. Essential for making each row unique within a table. Necessary for selecting individual rows, such as unique customers or products. Critical for web shops to distinguish between products. 2. Choosing primary keys. Selected from candidate keys or a surrogate key added by the developer. Debate exists between using logical, business, keys and surrogate keys. Data Vault modeling prefers business keys, while most other techniques prefer surrogate keys. 3. Advantages of surrogate keys. Better stability. Surrogate keys remain stable and unaffected by external changes. Example, transition from SOFI to BSN numbers in the Netherlands would require changes in multiple tables if using business keys. Surrogate keys are immune to such changes as they are internally managed and meaningless. No need to change. Surrogate keys do not require changes, unlike business keys which might change due to errors or external factors. Example, correcting a typo in an SSN used as a primary key involves updating multiple tables and rechecking uniqueness, which is time-consuming and resource-intensive. Surrogate keys avoid these issues. Better performance. Surrogate keys enhance database performance, especially crucial for operational databases like web shops. Numerical surrogate keys are efficient in memory usage and storage. 3 levels of performance improvement. Data loading and entering new data. Joining data. Reducing the actual size of tables. 4. Primary key impact. Affects performance and scalability of the database. Ensures efficient data management and retrieval, especially with increasing data volume and concurrent users. 1. Performance when loading data or entering new data. Key uniqueness check is faster with a small, efficient key. Faster insert rate for new data with small primary keys. Ascending order of key values improves insert performance. Surrogate keys typically follow this ascending order naturally. Note: loading new data is faster with small primary keys that always increase in value. 2. Performance when joining data. Primary keys are used as foreign keys in other tables for data combination. Combining tables requires key comparisons for matching rows. Large keys, e.g., 128 bits, require more CPU cycles compared to smaller keys, e.g., 64 bits. Surrogate keys allow for consistently small key sizes, typically integers fitting within 64 bits. Business keys depend on the actual data size, which can be larger and less efficient. 3. General considerations. Small databases with few users may not be significantly impacted by suboptimal choices. Making good design choices initially is as easy and cost-effective as not caring. Changing an operational database later is expensive and potentially disruptive. Ensuring your database can scale with growth is crucial. Minor performance enhancements can collectively have a significant impact. 1. Table size and efficiency. Large tables can store millions or billions of rows. Using shorter keys, e.g., product numbers, saves significant space compared to longer keys, e.g., product names. Example, a supermarket table with product numbers saves 22 bytes per row compared to using product names, resulting in a 22 gigabyte savings with a billion rows. Inefficient keys increase database size, storage costs, and memory requirements. 2. Surrogate keys versus business keys. Surrogate keys are generally preferred due to better stability, performance, and efficiency. Surrogate keys provide stability and do not change, avoiding issues like changing all occurrences in the database. Are typically small, numerical values, e.g., int, that enhance performance and efficiency. Avoid large, inefficient business keys that can slow down performance. Disadvantage: surrogate keys do not inherently check for uniqueness in other columns, potentially leading to business-level duplicates. 3. Primary keys ensure uniqueness of rows, allowing individual row operations read, change, delete. Critical for referencing unique rows due to SQL's set-based nature. 4. Foreign keys provide integrity by linking data across multiple tables. Enable meaningful data merging from different tables. Ensure referential integrity, maintaining relationships between tables. 5. Practical considerations. Using surrogate keys is generally better for most tables and databases. Data vault modeling is an exception where business keys might be preferred. Proper key choice at design time is crucial for future scalability and performance. Changing an existing database is difficult and costly, highlighting the importance of initial design decisions. 6. Integrity and data quality. Foreign keys help improve data quality by ensuring relationships between tables. Primary and foreign keys make database operations straightforward and reliable. Knowledge of primary and foreign keys is essential for writing efficient SQL queries. 1. Table creation. DBO, invoice table. Columns, invoice NR, int, not null, invoice date, date, not null, customer ID, int, not null, sales amount, money, not null. The table creation does not include primary or foreign keys initially. 2. Primary key addition. Alter table for primary key. Adds a primary key constraint on invoice NR, PK_invoice. Ensures uniqueness of invoice NR values. This statement fails if there are duplicate values in invoice NR before execution. 3. Foreign key addition. Alter table for foreign key. Adds a foreign key constraint on customer ID, FK_invoice_customer. Ensures customer ID in DBO. Invoice references existing customer ID in DBO, customer. This statement fails if customer ID values in DBO, invoice do not match any in DBO, customer. 4. Referential integrity. Definition. Ensures all foreign key values reference existing primary key values. Guarantees consistency between related tables. Checks performed. When adding a new row to DBO, invoice, it checks if customer ID exists in DBO, customer. When changing customer ID in DBO, invoice, it checks for existence in DBO, customer. When deleting a customer, it checks if there are related invoices. Deletion fails if related invoices exist. 5. Behavior and error handling. Default behavior. Throw errors when referential integrity checks fail. Customization. Possible to change the default behavior by adding extra properties to the foreign key. 6. Summary of code functionality. Lines 1 to 7. Create DBO, invoice table with 4 columns. Lines 9 to 10. Add primary key constraint on invoice NR. Lines 12 to 14. Add foreign key constraint on customer ID, ensuring referential integrity with DBO, customer.